October 2025 marks the first time in recorded history that two separate cosmic objects are simultaneously racing toward the Sun from completely different origins. 3I Atlas confirmed interstellar wanderer carries a chemical signature that breaks the rules of stellar formation. Meanwhile, Swan R2 has brightened so rapidly, it suggests a composition unlike anything from our own Oort cloud. Their combined approach creates a celestial traffic jam that mathematically should happen once every few million years. Yet here they are both scheduled for solar encounters within 28 days of each other. Ground control is tracking trajectories that converge with mechanical precision. The instruments detect chemical anomalies that challenge decades of comet science. But here's where it gets interesting. As both objects sink deeper into solar glare, our telescopes will go completely blind during the most critical phases of their encounters. What if this timing isn't coincidental? What if something doesn't want us watching? Stay with me as we explore why October 2025 could rewrite everything we think we know about what's really going on out there. Part 1. Two lights in the sky. Two strangers have arrived in our solar system. One slender and swift, tinged with an otherworldly green glow, the other sprawling and brilliant, unfurling a tail that stretches across degrees of sky. They came from different corners of space, yet here they are converging on our Sun in a cosmic choreography that has astronomers checking their calculations twice. The first visitor materialized on July 1, 2025 in the digital eyes of the Atlas Survey Telescope in Chile. A single pixel of light that shouldn't have been there. Within hours, orbital mechanics revealed the truth. This object, designated 3I Atlas, was moving on a hyperbolic trajectory not bound to our Sunday. An interstellar wanderer, the third confirmed visitor from beyond our solar system's edge. The second appeared just months later, emerging from the solar glare like a ghost, materializing at dawn. Comet C 2025 R2 discovered in Swan imagery on September 11, 2025. Already bright enough for binoculars, already sporting a tail that amateur astronomers were calling magnificent. In the sterile halls of NASA's Jet Propulsion Laboratory, computers hum with the constant whisper of telemetry. Radio dishes across the globe track these visitors with the mechanical precision of a heartbeat. Each data packet tells a story, brightening curves, spectral signatures, orbital refinements, measured to the 10th of an astronomical unit. But numbers, however precise, cannot capture what hangs in the night sky above us. Stand outside on a clear October evening away from the city's orange glow, and you might glimpse them both. 3I Atlas appears as a faint smudge through a modest telescope, its green tint subtle but unmistakable to trained eyes. Swan R2 dominates the western horizon after sunset, its tail sweeping upward like a cosmic brushstroke painted against the darkening sky. The instruments speak in frequencies we cannot hear, the staccato tick of CCD shutters capturing photons that traveled millions of years to reach us. The electronic whisper of spectrographs decomposing starlight into its constituent elements. Ground stations worldwide relay their findings in data streams that flow like digital rivers toward analysis centers where human minds struggle to interpret what their machines are seeing. But space itself remains silent. No sound carries across the vacuum between worlds. Only electromagnetic radiation bridges the gap, carrying information encoded in wavelengths of light that tell us these objects are not quite what they appear to be. 3. Atlas moves with the purposeful speed of something that knows where it's going. Its trajectory carries it on a path that will bring it closest to our Sun on October 29, 2025, 1.35 astronomical units from our star just inside Mars's orbit. For an interstellar visitor, this represents a remarkably close approach. Close enough that some are beginning to ask uncomfortable questions. Swan R2 follows its own schedule. It reached perihelion on September 12, 2025, diving to within half an astronomical unit of the Sun before beginning its outward journey. But its closest approach to Earth comes later, October 21st, when it will pass within 0.27 astronomical units of our world. In cosmic terms, this is practically skimming our atmosphere. The timing is what keeps astronomers awake at night, staring at their computer screens long after their colleagues have gone home. Two objects from completely different origins converging on our inner solar system within weeks of each other. The mathematics of probability suggest this should be extraordinarily rare. Yet here we are, witnesses to what may be the most remarkable coincidence in recorded astronomical history. Or perhaps it isn't a coincidence at all. The green tint of 3 Atlas has captured particular attention. Spectroscopic analysis reveals the presence of diatomic carbon and cyanogen molecules that fluoresce green when excited by solar radiation. Natural enough for a comet beginning to outgas as it approaches our star. But the intensity and consistency of this coloration has raised eyebrows among researchers who have spent their careers studying these celestial wanderers. Swan R2 presents its own mysteries. Its rapid brightening as it emerged from solar conjunction suggests a composition unlike typical comets from our own Oort cloud. The tail development follows patterns that are familiar yet somehow different, as if following a script written in a slightly foreign language. Scale matters in space, and the contrast between our visitors could hardly be more dramatic. 3I Atlas appears as a needle of light, compact and purposeful. Current estimates suggest a nucleus perhaps a few kilometers across modest by cometary standards, yet sufficient to generate the activity we observe. Swan R2, by contrast, spreads across the sky like a luminous veil, its coma and tail spanning degrees of arc when viewed from Earth. We are entering October 2025 with 2 cosmic visitors racing toward their closest encounters with our Sunday. Mars will get a front row seat to 3I Atlas on October 3rd when the red planet's orbital path brings it within 30 million kilometers of the interstellar wanderer. Our robotic emissaries orbiting Mars, the cameras and spectrometers we've placed there, will turn their instruments toward this approaching visitor gathering data that may finally answer some of the questions that keep growing with each observation. But there's a problem with October. As both objects approach their closest encounters with our Sun, Earth's viewing geometry becomes increasingly challenging. Solar glare will eventually swallow both visitors, leaving our ground-based telescopes blind during the most critical phases of their journeys. For weeks, possibly months, we will lose sight of them entirely. When they emerge from behind our star, if they emerge at all, what story will the instruments tell? Will they be unchanged, bearing only the expected scars of their solar encounters, or will they carry with them evidence of something more profound, something that challenges our understanding of what moves through the spaces between stars? The question that haunts these October nights is deceptively simple, yet impossibly complex. Is it a comet, a fortress, or the reply to a message we never knew we sent? The universe has placed 2 mysteries in our sky, and October 2025 may be our only chance to solve them before they disappear forever into the cosmic dark. But first, we need to understand how we found them, and more importantly, how they found us. Part 2: Instruments that Whisper. The discovery of cosmic visitors begins not with a dramatic moment of revelation, but with the patient accumulation of photons on silicon sensors scattered across our planet. Each night, automated telescopes scan predetermined patches of sky, their electronic eyes capturing images that will be compared, processed, and scrutinized by algorithms designed to notice what shouldn't be there. The Atlas survey that found 3I Atlas operates 4 telescopes spread across 2 continents, each equipped with cameras capable of monitoring vast swaths of sky simultaneously. Every clear night, they generate hundreds of gigabytes of data, millions of stellar positions, measured to extraordinary precision. The discovery of an interstellar visitor emerges from this flood of information as a single anomalous point of light that moves too fast and in the wrong direction. But Atlas is just one voice in a global chorus of automated sentinels. The Catalina Sky Survey in Arizona, Linear in New Mexico, NEO eyes orbiting high above Earth's atmosphere all contribute to a network of eyes that never sleep, never blink, never miss a shift in the cosmic order. When Swan R2 appeared in the data from the Solar and Heliospheric Observatory, it wasn't NASA's professional astronomers who first noticed it. Amateur astronomer Vladimir Bezugli, examining swan imagery for his own research, spotted the anomalous brightening that would become one of the most spectacular comets of 2025. This is how modern astronomy works. Professional and amateur observers, silicon sensors, and human intuition all working together to catch the fleeting moments when something new enters our cosmic neighborhood. The instruments whisper their secrets in the language of photon counts and pixel intensities, but it takes human insight to recognize when those whispers are trying to tell us something extraordinary. Different types of instruments reveal different truths about our celestial visitors. Visible light cameras show us the overall structure, the brightening nucleus, the expanding coma, the sweeping tail that points away from the sun like a cosmic weather vane. But to understand what these objects truly are, we need to break their light apart into its constituent colors. Spectroscopy transforms starlight into information. When molecules in a comet's coma absorb and remit solar radiation, they create distinctive fingerprints in the spectrum of light we receive. The Very Large Telescope's observations of 3I Atlas revealed unexpected details, strong emission lines from cyanogen, and more surprisingly from nickel atoms glowing in the vacuum of space. The presence of nickel is not unprecedented in comets, but it's unusual enough to warrant attention. More intriguing is what the VT didn't detect: iron emission lines that typically accompany nickel in natural samples. The absence of iron combined with the strong nickel signature creates a chemical fingerprint that doesn't quite match expectations based on our understanding of how comets form and evolve. The James Webb Space Telescope turned its infrared eyes toward 3I Atlas in August 2025, revealing a composition dominated by carbon dioxide, with relatively little water vapor, at least at the large distances where these observations were made. This is consistent with a comet whose outer layers are rich in volatile ices that sublimate at lower temperatures, creating activity long before water ice begins to contribute significantly to the observed coma. SWAN imagery provides yet another perspective. The Solar and Heliospheric Observatory's SWAN instrument maps the distribution of hydrogen atoms created when water molecules are broken apart by solar ultraviolet radiation. This gives us a three-dimensional view of how water vapor spreads through space around active comets, revealing details invisible to conventional telescopes. The Hubble Space Telescope contributed high-resolution imagery that constrains the size of 3I Atlas's nucleus to perhaps a few kilometers across, substantial enough to generate the observed activity, but small enough to have escaped detection until it was already well into our solar system. Each observation adds another piece to a puzzle that grows more complex with every dataset. But instruments can deceive as well as reveal. The automated processing systems that analyze telescopic imagery are designed to recognize known patterns, the predictable behavior of objects following Keplerian orbits around the Sunday. When something behaves differently, even subtly, those differences can be masked by the very algorithms designed to make sense of the data. Consider the challenge of measuring brightness changes. Comets don't brighten steadily as they approach the Sunday. Instead, they undergo complex variations driven by the sublimation of different ice at different distances, the rotation of irregularly shaped nuclei, and the episodic release of dust and gas from active regions. Distinguishing between natural variability and genuinely anomalous behavior requires careful analysis by experts who understand the Anaya subtleties of cometary physics. The green coloration observed in 3I Atlas illustrates this complexity. Several molecules can produce green emission under the conditions found in cometary comas. Diatomic carbon is the most common culprit, fluorescing green when excited by solar radiation. Cyanogen can also contribute to green coloration. Without high-resolution spectroscopy to definitively identify the responsible molecules, the green tint remains suggestive rather than diagnostic. Media coverage of unusual astronomical discoveries tends to amplify uncertainty into sensation. When preliminary reports mention unexpected chemical signatures or unusual orbital characteristics, those details can be transformed into evidence for extraordinary interpretations long before peer review has had a chance to validate or refute the initial observations. The scientific process is designed to be self-correcting, but that correction often happens more slowly than public interest demands answers. This is where the instruments become most important, not just as detectors of cosmic phenomena, but as anchors to reality in a sea of speculation. The telescopes don't care about human desire for dramatic discoveries. They simply record photons and measure positions, building up a database of observations that will eventually reveal the truth about our visitors. Safety considerations add another layer to these observations. Both 3I Atlas and SWAN are to follow trajectories that keep them safely distant from Earth. 3I Atlas will approach no closer than 1.8 astronomical units, about 270 million kilometers. SWAN R2's closest approach brings it within 0.27 astronomical units, still more than 40 million kilometers away. These are not threats to our planet, but opportunities to study objects that formed in conditions very different from our own solar system. The challenge now is time. As October 2025 progresses, both visitors will sink deeper into solar glare as seen from Earth. Ground-based telescopes will lose the ability to track them during the most interesting phases of their solar encounters. Space-based observatories fare better, but have limited observing time and must balance these targets against other scientific priorities. What emerges from this instrumental chorus is a picture painted in data points and spectral lines, orbital elements, and brightness curves. But pictures can be interpreted in many ways. And the question remains, what if the first deceived were the instruments or the expectations of the people reading them? The telescopes will continue their patient vigil, accumulating photons and measuring positions with mechanical precision. But as our visitors sink toward the sun, the instruments' whispers will grow fainter, leaving us to wonder what secrets might be hidden in the growing silence. Part 3. The language of metals. Deep space speaks in the vocabulary of atoms. And 3. Atlas is telling us a story written in an unexpected dialect. When the Very Large Telescope turned its powerful spectrographs toward this interstellar visitor, it discovered something that made astronomers pause and recalculate their expectations. Nickel vapor glowing in the near vacuum around the comet's nucleus, unaccompanied by the iron emissions that should have been there. In the realm of spectroscopy, every element writes its signature in light. When atoms are excited by solar radiation or collisional processes, they emit photons at very specific wavelengths, fingerprints as unique and identifiable as human DNA. Nickel atoms produce emission lines in the green portion of the spectrum, contributing to the ethereal coloration that has made 3I Atlas a favorite target for astrophotographers. But nickel rarely travels alone in the cosmos. In meteorites, asteroids, and the few comets where it has been detected, nickel typically appears alongside iron in ratios that reflect the nuclear processes that forged these elements in stellar cores billions of years ago. The cosmic abundance patterns written into the periodic table suggest that where you find nickel iron should follow in predictable proportions. 3. Atlas seems to have missed that particular chemistry lecture. The VT observations conducted as the comet approached its August 2025 brightness peak revealed strong nickel emission lines that stood out clearly against the background spectrum. The same observations looked for iron and found essentially nothing. The upper limits were so low that if iron were present in normal cosmic abundances, it should have been easily detectable. This chemical peculiarity has spawned numerous theoretical explanations, each attempting to reconcile the observations with known physics. Perhaps nickel-bearing organic compounds stable in the cold of interstellar space break down under solar heating to release nickel atoms preferentially. Perhaps space weathering processes over millions of years have altered the surface chemistry of this wandering iceberg in ways we don't fully understand. The universe is under no obligation to conform to human expectations about how elements should behave. Comet 2E Borisov, the previous interstellar visitor, displayed its own chemical oddities when analyzed by the world's most powerful telescopes. Its carbon monoxide to water ratio differed significantly from comets born in our own solar system, suggesting formation in a colder, more carbon monoxide-rich environment around its parent star. But 3 Atlas pushes these chemical anomalies into more intriguing territory. The James Webb Space Telescope's infrared observations revealed a composition dominated by carbon dioxide, with water vapor playing a surprisingly minor role at the large distances where these measurements were made. This pattern, carbon dioxide leading the volatility parade, followed eventually by water, as the comet approaches closer to the sun, suggests an onion-like layered structure with the most volatile ices on the outside. Cyanogen, the molecule likely responsible for much of the green coloration, adds another layer to this chemical portrait. CN emission lines appear prominently in the spectrum, consistent with organic compounds being broken apart by solar ultraviolet radiation. But the relative strengths of different emission features don't quite match the pattern seen in solar system comets, suggesting subtle differences in composition or structure. The green tint that has captured public attention carries its own mysteries. While diatomic carbon is often cited as the primary source of green coloration in comets, the specific molecules responsible for 3I Atlas's verdant glow remain uncertain. Cyanogen can contribute green emission, so can certain excited states of carbon molecules. Without ultra-high-resolution spectroscopy to definitively identify the culprits, the green remains beautifully ambiguous. These chemical signatures translate into a narrative that challenges simple classification. If atoms are letters and molecules are words, then 3-Atlas writes in a dialect heavy on carbon dioxide and touched with metallic accents that don't quite follow terrestrial grammar. It's a composition that makes sense in the context of comet formation around other stars, but unusual enough to warrant the attention it's receiving. The production rates of different gases provide another clue to the visitor's nature. As 3I-Atlas approaches the Sun, the rate at which it produces various molecules increases predictably with decreasing distance. This follows the expected pattern for sublimating ices. The closer to the Sun, the more rapidly frozen volatiles transform directly from solid to gas. The mathematics of this process are well understood, making it possible to predict future activity levels based on current observations. Yet within this predictable framework, subtle anomalies persist. The ratios between different molecular species don't exactly match models based on solar system comets. The brightness curve shows variations that suggest either compositional inhomogeneities across the nuclear surface, or perhaps discrete outgassing events triggered by subsurface processes we can only guess at. The amateur astronomy community has contributed significantly to characterizing these chemical mysteries. High-quality imagery from backyard observers around the world documents the evolution of the coma structure and tail morphology as 3I-Atlas continues its approach to perihelion. These observations provide temporal coverage that professional telescopes, with their limited observing time and competing research priorities, cannot match. Social media has amplified certain aspects of these chemical anomalies, sometimes transforming preliminary scientific results into sensational headlines that outpace the actual data. The nickel without iron observation, for instance, has been interpreted by some as evidence of artificial construction metallic components designed rather than accreted. This interpretation requires extraordinary leaps beyond what the spectroscopic data actually supports. NASA's position remains clear. Current observations are consistent with a natural cometary visitor, albeit one with unusual but not unprecedented chemical characteristics. The agency's scientists emphasize that chemical peculiarities are expected for objects formed around other stars where different temperatures, pressures, and elemental abundances could produce compositions unlike anything in our own solar system. The European Space Agency, through its various missions and ground-based observing campaigns, has reached similar conclusions. While acknowledging the unusual aspects of 3I-Atlas's spectrum, ESA researchers note that the fundamental physics of cometary activity, sublimating, is producing observed gas and dust, provides a coherent framework for understanding these observations without invoking exotic explanations. But science progresses through the careful examination of anomalies, and 3-Atlas presents enough chemical curiosities to keep researchers busy for years to come. The nickel emissions, the carbon dioxide dominance, the cyanogen signatures, the green coloration. Each observation adds another piece to a puzzle that may ultimately teach us as much about stellar system formation as it does about this particular visitor. As October 2025 progresses and 3I-Atlas sinks toward solar conjunction, the opportunities for detailed spectroscopic analysis are diminishing. The combination of increasing distance from Earth and decreasing solar elongation will eventually make ground-based observations impossible, at least until the comet emerges from behind the Sun months later, if it emerges at all. If chemistry is a language, then we are reading a dialect of ice and metal that speaks of formation, conditions perhaps hundreds of light years from here. Whether that syntax follows the grammar of physics and chemistry as we understand them, or hints at something more deliberately constructed, remains the central mystery of our October sky. The atoms don't lie, but they don't necessarily tell us everything we want to know either. Part 4. 2 paths. 1 dance. Picture the solar system as a vast clockwork mechanism with planets tracing their predictable ellipses around our central star, while smaller bodies, asteroids, comets, and the occasional interstellar wanderer follow trajectories that intersect and diverge according to the mathematics of gravitational mechanics. Now imagine two visitors arriving from completely different directions, following completely different types of orbits, yet timing their closest approaches to our Sun within weeks of each other. The probability of such a coincidence should be vanishingly small. Yet here we are in October 2025, watching exactly this scenario unfold above our heads. 3I Atlas emerged from the direction of the constellation Serpens Cauda in early July. Its discovery marking the moment when this interstellar visitor became bright enough for our automated sky surveys to detect. Its orbit carries it on a hyperbolic trajectory, the mathematical signature of an object not gravitationally bound to our Sunday. With an orbital inclination of approximately 175 degrees, it's traveling retrograde relative to the planets approaching our solar system from underneath the ecliptic plane like a cosmic salmon swimming upstream against the current of planetary motion. Swan R2 tells a different story entirely. This object belongs to the class of long-period comets visitors from our own Oort cloud that spend most of their existence in the cold outer reaches of the solar system before gravity nudges them into the inner regions where solar heating brings them to life. It appeared near the constellation Virgo, emerging from the solar glare that had hidden it from our view during its approach. The geometries of their discoveries reveal important clues about the nature of both objects. 3. I-Atlas remained hidden until it was already well into our solar system because interstellar visitors approach from arbitrary directions, often spending months or years in regions of sky too close to the Sun for effective observation. By the time Atlas found it, this cosmic wanderer was already past the orbit of Jupiter and beginning to show the first signs of cometary activity. Swan R2 suffered from a different observational bias known as the Holetschek effect. Long-period comets often brighten dramatically as they approach the Sun, but this brightening occurs while they're still at small angular separations from our star as seen from Earth. They remain hidden in solar glare until their orbits carry them far enough from the Sun's line to become visible in twilight skies, which is exactly what happened with Swan R2 in September 2025. The timing convergence of their key milestones creates a cosmic schedule that reads like someone planned it. Swan R2 reached perihelion on September 12th, diving to within 0.5 astronomical units of the Sunday. 3I Atlas will make its closest approach to Mars on October 3rd, passing within 30 million kilometers of the red planet. 3I Atlas reaches its own perihelion around October 29th or 30th, approaching within 1.35 astronomical units of our star. Swan R2's closest approach to Earth occurs around October 21st, when it will pass within 0.27 astronomical units of our world. This clustering of significant events within a 6-week window stretches the boundaries of coincidence theory. If these were random events distributed uniformly across time, the probability of such tight temporal correlation would be extraordinarily low. Yet statistical mechanics also teaches us that extremely unlikely events become virtually inevitable, given sufficient time and sufficient opportunities. In a universe containing billions of comets and occasional interstellar visitors, perhaps we're simply witnessing one of those rare moments when the dice roll in an unexpected pattern. The contrast between our visitors extends far beyond their origins and orbits. 3I Atlas appears as a compact needle of light, its activity confined to a relatively small region around its nucleus. Current estimates suggest a nucleus perhaps a few kilometers in diameter, substantial enough to generate the observed coma and tail, but modest compared to the largest comets in our own solar system. Swan R2 presents itself as a cosmic spectacle of entirely different proportions. Its coma spans degrees of sky when viewed through binoculars, and its tail has been reported extending up to 2 degrees in length by experienced observers. This represents a physical scale measured in millions of kilometers, a gossamer structure so tenuous that its density approximates a laboratory vacuum, yet visible across interplanetary distances due to the sheer volume of space it occupies. The visual poetry of their convergence plays out against the backdrop of Earth's changing seasons. As autumn progresses in the northern hemisphere, both objects sink lower toward the western horizon after sunset. Swan R2 dominates this celestial theater, easily visible to anyone with a decent pair of binoculars and a clear view toward Virgo. 3I Atlas requires more serious equipment to observe, but its green tint makes it unmistakable once located. But October brings challenges as well as opportunities. The same geometries that create these close solar encounters also conspire to make detailed observations increasingly difficult. As both objects approach their perihelion passages, they sink deeper into solar glare as viewed from Earth. Ground-based telescopes will eventually lose the ability to track them during the most scientifically interesting phases of their journeys. This observational blackout period represents more than just an inconvenience. It's a gap in our knowledge that may prove crucial to understanding what these visitors truly represent. During the weeks when Earth-based telescopes cannot observe them, both objects will undergo their most intense solar heating. If anything unusual is going to happen, if any hidden characteristics are going to reveal themselves, it will likely occur during these invisible weeks. The retrograde motions of 3I Atlas adds another layer of complexity to its orbital mechanics. Objects moving retrograde relative to the planets experience different patterns of gravitational perturbation, potentially affecting their long-term trajectories in subtle but measurable ways. These effects could be used to constrain the visitor's mass and internal structure, provided we can track it accurately enough before and after its solar encounter. Mars serves as our forward observer during 3I Atlas's October 3rd closest approach. The Red Planet suite of orbiting spacecraft missions designed to study Martian weather and geology will turn their instruments toward this passing visitor. The observations will be opportunistic rather than planned, but they may provide our only clear view of 3I Atlas during its critical solar approach phase. The European Space Agency has announced plans for Mars-based observations using the ExoMars Trace Gas Orbiter and other assets in orbit around the Red Planet. These spacecraft carry spectrometers and imaging systems that could potentially resolve details invisible from Earth-based telescopes. The viewing geometry from Mars will be favorable during the flyby, offering perspectives on the comet's coma structure and tail development that complement our Earth-based observations. Yet even with multiple viewpoints and sophisticated instruments, fundamental questions remain unanswered. The coincidence of timing continues to nag at researchers who have spent their careers studying the statistical mechanics of solar system dynamics. In a cosmos where chance encounters span millions of years, why are we witnessing two such dramatically different visitors arriving virtually simultaneously? If two paths rhyme, is it poetry or a plan? Part 5. Theories laid on like constellations. Human minds are pattern-seeking machines evolved to find meaning in chaos and purpose in randomness. When confronted with two cosmic visitors arriving at our sun within weeks of each other, displaying unusual characteristics and following trajectories that seem almost choreographed, those minds begin constructing narratives that extend far beyond what the data actually supports. These stories range from the merely exotic to the frankly extraordinary, each offering a different lens through which to view the October 2025 convergence. The Scout and Fortress hypothesis positions 3I Atlas as an advanced reconnaissance probe, swift and maneuverable, tasked with surveying our solar system's resources and defenses. Swan R2 in this scenario serves as the main installation, a mobile base or communications relay capable of supporting extended operations out in our inner solar system. The timing of their arrivals isn't coincidental, but coordinated, representing phases of a larger mission that began years or decades ago in the cold spaces between stars. A maintenance run interpretation suggests both objects are part of an ancient infrastructure automated systems that follow predictable cycles to service equipment or update programming scattered throughout our local galactic neighborhood. 3. Atlas might carry software updates or replacement components, while Swan R2 provides the manufacturing capability or power resources necessary for major system overhauls. Our solar system in this view is merely one stop on a regular service route. The ancient patrol concept imagines these visitors as remnants of a monitoring network established millions of years ago by a civilization concerned with the development of potentially dangerous intelligence in their cosmic neighborhood. As our radio emissions began leaking into space over the past century, dormant systems might have activated, dispatching both reconnaissance elements and more substantial platforms to assess the threat level represented by emerging human technology. Perhaps most provocatively, some suggest these objects represent a reply to humanity's unintentional message to the stars. Our radio and television broadcasts, radar systems, and satellite communications have been expanding outward at light speed for decades, creating an ever-growing bubble of electromagnetic signature around our planet. If someone or something has been listening, 3I Atlas and Swan R2 might constitute their response, arriving not randomly, but in direct reaction to our technological coming of age. The relic technology hypothesis proposes these might be artifacts of human civilization itself, launched during some future era, when our descendants achieved interstellar capabilities, then sent back through time or along trajectories designed to arrive at specific moments in our past. The unusual chemistry and orbital characteristics could reflect manufacturing techniques or material science beyond our current understanding, yet still recognizably human in origin. Mythological interpretations draw parallels to ancient stories of celestial harbingers, comets, and unusual astronomical phenomena that preceded major historical transitions. Every culture on Earth has legends of lights in the sky that announce the rise and fall of kingdoms, the coming of prophets, or the end of ages. Perhaps 3I Atlas and Swan R2 represent a modern manifestation of these archetypal patterns, cosmic punctuation marks that separate one era of human development from the next. The Predator and Guardian dynamic offers a more ominous perspective. If 3I Atlas represents a threat, a weapon system, or invasion probe, then Swan R2 might be a defensive response, either deployed by the same civilization as a safeguard against their own technology, or dispatched by a different intelligence to neutralize the danger before it reaches us. The October 2025 convergence becomes a celestial battlefield, with Earth as the unwitting prize. These speculative frameworks gain traction partly because they address a fundamental limitation of conventional astronomy, the assumption that unusual phenomena must have natural explanations. This assumption has served science well, driving discoveries from stellar evolution to black hole physics. But it also creates blind spots, areas where exotic possibilities are dismissed, not because evidence contradicts them, but because they fall outside accepted theoretical frameworks. Avi Loeb, the Harvard astronomer who gained international attention for his suggestions about 1I Oumuamua's potentially artificial nature, has extended similar arguments to 3I Atlas. He points to the unusual chemical signatures, the precise timing of the solar approach, and the apparent coordination with Swan R2 as potential indicators of technological rather than natural origins. His arguments emphasize that extraordinary claims require extraordinary evidence, but also that extraordinary evidence, when it appears, deserves extraordinary consideration. NASA and the European Space Agency maintain more conservative positions, emphasizing that current observations remain consistent with natural explanations despite their unusual characteristics. Agency scientists note that our sample of interstellar visitors remains extremely small, just 3 confirmed objects over the past 6 years, making it difficult to establish what should be considered normal or anomalous for this population. The tension between these perspectives reflects deeper questions about scientific methodology and the nature of evidence itself. How unusual must an observation be before we seriously consider explanations that challenge our fundamental assumptions about the universe? How do we balance scientific conservatism against the risk of missing genuinely revolutionary discoveries? Media coverage has amplified certain aspects of these debates while downplaying others. The nickel without iron observation receives breathless coverage on social media platforms, often accompanied by speculation about industrial processes or manufacturing signatures that goes far beyond what the spectroscopic data actually supports. Meanwhile, the genuine scientific puzzles posed by 3 Atlas, the unusual volatile composition, the precise orbital timing, the coordination with Swan R2, receive less attention despite being more solidly grounded in observational data. The psychology of conspiracy thinking also plays a role in how these theories develop and spread. Humans are predisposed to see agency and intention in random events, particularly when those events seem to have significant implications for our future. The idea that cosmic visitors might be deliberately sent rather than randomly encountered satisfies deep psychological needs for meaning and control in an apparently chaotic universe. Historical precedents provide both caution and encouragement for exotic interpretations. Every genuinely revolutionary astronomical discovery, from heliocentrism to black holes to exoplanets, initially faced skepticism from established scientific communities. But history also shows that extraordinary claims without extraordinary evidence typically fade into obscurity, leaving behind cautionary tales about the dangers of premature speculation. The October 2025 convergence offers an opportunity to test these competing hypotheses against real data. If 3I, Atlas, and Swan R2 are natural comets following predictable physical laws, their behavior during perihelion passage should conform to well-established models of ice sublimation and dust emission. If they represent something more exotic, the deviations from expected behavior should become apparent during their closest approaches to the Sunday. But there's a catch. The same solar glare that makes perihelion passages so scientifically interesting also makes them difficult or impossible to observe from Earth. During the most critical phases of their solar encounters, both objects will be hidden from our ground-based telescopes, leaving us to infer what happened based on their condition when they emerge from behind the Sun, if they emerge at all. This observational gap creates space for speculation to flourish unchecked by data. In the absence of direct measurements, any theory becomes possible, any interpretation becomes plausible. The October silence may tell us as much about human psychology as it does about cosmic visitors. Regardless of which theoretical framework ultimately proves correct, the convergence of 3I Atlas and Swan R2 represents a moment of genuine scientific opportunity. Whether they turn out to be exotic ice balls or something far stranger, they're expanding our understanding of what exists in the spaces between stars and what might occasionally find its way to our cosmic neighborhood. The theories we construct around them say as much about our hopes and fears as they do about the objects themselves. But perhaps that's exactly as it should be. Is it a comet, a fortress, or the reply to a message we never knew we sent? Part 6. 3 Atlas Discovery and Trajectory. The story of 3 Atlas begins with a single pixel changing brightness on a CCD detector in the Atacama Desert of northern Chile. July 1, 2025 marked the moment when this interstellar wanderer finally became bright enough for our automated sky surveys to distinguish it from the background stars that have held steady in their positions for millennia. The Atlas Survey Asteroid Terrestrial Impact Last Alert System operates 4 robotic telescopes designed primarily to detect potentially hazardous asteroids that might threaten Earth. These mechanical sentinels scan the sky methodically, comparing each night's observations against catalogs of known objects to identify anything that moves, brightens, or appears where nothing existed before. When the Atlas telescope at El Sos captured that first detection of 3I Atlas, the object appeared as nothing more than a faint smudge moving against the stellar background. But motion in space tells stories, and within hours of discovery, orbital calculations revealed something extraordinary. This newcomer was traveling on a hyperbolic trajectory unbound to our sun's gravitational embrace. The mathematics of orbital mechanics divide all celestial objects into 2 fundamental categories: those that belong to our solar system, following elliptical paths that eventually bring them back to where they started, and those that are merely passing through, following hyperbolic trajectories that carry them past our sun once and then out into the cosmic void forever. 3I Atlas falls definitively into the second category, marking it as only the 3rd confirmed interstellar visitor in recorded human history. Its orbital characteristics tell the story of a journey that began in the spaces between stars. The trajectory carries an inclination of approximately 175 degrees relative to the plane of Earth's orbit, meaning it approaches our solar system from underneath, traveling retrograde relative to the motion of the planets. This is the signature of an object that formed elsewhere in a different stellar system with different physical conditions, then spent millions of years crossing the interstellar void before arriving in our cosmic neighborhood. The discovery timeline reveals how close we came to missing this visitor entirely. Interstellar objects approach from random directions in space, often spending months or years in regions of sky too close to the sun for effective observation from Earth. By the time Atlas detected 3I Atlas, it had already passed through the outer reaches of our solar system and was beginning its final approach toward perihelion. Backtracking the orbital calculations suggest this wanderer has been within our solar system since early 2025, perhaps even late 2024, gradually brightening as it approached the Sun and began to show the first signs of cometary activity. The delayed discovery illustrates one of the fundamental challenges of interstellar object detection. We can only find them when they become bright enough and positioned favorably enough for our instruments to distinguish them from the background stars. Current projections place three I-Atlas's closest approach to the Sun, its perihelion, around October 29th or 30th, 2025, at a distance of approximately 1.35 to 1.4 astronomical units. To put this in perspective, this places the visitor just inside the orbit of Mars, closer to our star than any previous interstellar object has been observed to approach. The trajectory will carry three I-Atlas past Mars on October 3rd, 2025, at a distance of roughly 30 million kilometers. While this represents a distant flyby in human terms, it's close enough for the sophisticated instruments aboard our Martian spacecraft to potentially observe the visitor during this critical phase of its solar approach. The European Space Agency has announced preliminary plans to use Mars orbiting assets for opportunistic observations as during this encounter. For Earth-based observers, 3 Atlas maintains a safe distance throughout its passage. The closest approach to our planet occurs at approximately 1.8 astronomical units, roughly 270 million kilometers away. This distance ensures that the visitor poses no threat to Earth while remaining accessible to our most powerful telescopes during favorable viewing periods. The size estimates for 3 I-Atlas remain uncertain, but suggest a relatively modest nucleus. Hubble Space Telescope observations conducted on July 21, 2025, constrained the object's dimensions to perhaps a few kilometers in diameter, substantial enough to generate the observed cometary activity, but smaller than many of the spectacular comets that have graced our skies in recent decades. This size estimate comes with significant uncertainties due to the challenges of observing such distant faint objects. The brightness we see results from sunlight scattered by dust and gas in the coma surrounding the nucleus, not from the nucleus itself. Determining the actual size requires careful modeling of how efficiently the nucleus reflects sunlight and how much material it's releasing into space through sublimation processes. The observational campaign coordinated around 3I Atlas represents one of the most intensive studies ever conducted of an interstellar visitor. The Hubble Space Telescope has provided high-resolution imagery tracking changes in coma structure and brightness over time. The James Webb Space Telescope turned its infrared capabilities toward the object in August, revealing details about its chemical composition that would be impossible to obtain from ground-based observations. The Very Large Telescope in Chile has contributed crucial spectroscopic data, breaking the visitor's light into constituent colors to identify the specific molecules and atoms glowing in its coma. These observations reveal the unusual chemical signatures, strong nickel emission without accompanying iron-prominent cyanogen lines and carbon dioxide dominance that have made 3I Atlas such a subject of scientific interest and public fascination. Multiple space telescopes continue tracking this visitor as it approaches its October encounters, but time is running short for detailed observations from Earth's vicinity. The combination of increasing distance and unfavorable solar elongation angles will eventually make ground-based observations impossible, leaving us dependent on whatever data our Mars-based assets can gather during the brief flyby window. The international coordination required for this observational campaign illustrates how modern astronomy operates as a global enterprise. Telescopes in Chile track the object during Southern Hemisphere nights, then hand off coverage to facilities in Hawaii and the Canary Islands as Earth's rotation carries the visitor into different viewing zones. Space-based observatories provide continuity across daylight cycles and atmospheric conditions that might block ground-based observations. But perhaps the most intriguing aspect of 3 Atlas's discovery involves what we almost missed. The visitor's faint nature and unfavorable early viewing geometry meant that for months, possibly years, it traveled through our solar system undetected. How many similar objects might have passed through without ever becoming bright enough or positioned favorably enough for our surveys to find them? The detection efficiency for interstellar visitors depends heavily on their size, composition, and trajectory. Objects that don't develop substantial comas might remain invisible until they pass very close to the sun, while visitors approaching from certain directions might be hidden in solar glare during their entire passage through the inner solar system. Statistical models suggest that for every interstellar object we detect, dozens or hundreds might pass through unobserved. 3I Atlas represents not just a singular discovery, but a glimpse into what might be a much larger population of cosmic wanderers crossing through our neighborhood on a regular basis. As October 2025 progresses, 3I Atlas continues its relentless approach toward perihelion now visible to experienced observers with modest telescopic equipment. Its green-tinged coma has become a distinctive feature in the autumn sky, a reminder that our solar system serves as a crossroads for travelers from distant stars. Before it vanishes into solar glare, Mars gets a front-row seat to whatever secrets this visitor might be carrying. The question remains whether our instruments, both on Mars and here on Earth, are sophisticated enough to distinguish between the exotic and the extraordinary in the brief time we have left to observe this remarkable cosmic wanderer. Part 7. Strange Colors and Strange Chemistry. The universe paints its stories in wavelengths of light, and 3 Atlas has been creating a masterpiece in green since its discovery. As this interstellar visitor approaches our sun, its nucleus heats up and begins releasing frozen gases that have been locked in ice for millions of years. But the palette emerging from this cosmic artist doesn't quite match the colors we expect from objects born in our own solar system. The green coloration that has captivated observers worldwide emerges from a complex interplay of chemistry and physics occurring in the near vacuum around the comet's nucleus. When molecules are excited by solar ultraviolet radiation or collisional processes, they emit light at very specific wavelengths determined by the quantum mechanical structure of their electron orbitals. For green emission, the most common culprits are diatomic carbon molecules and cyanogen radicals, both of which fluoresce brilliantly when bathed in sunlight. Live science coverage of the phenomenon has explored the leading candidates for this verdant glow, noting that while diatomic carbon remains the most likely explanation based on past cometary observations, the specific molecular species responsible for 3I Atlas's coloration have not yet been definitively confirmed through high-resolution spectroscopy. The distinction matters because different molecules tell different stories about the conditions under which this visitor formed and evolved. Cyanogen, a molecule consisting of carbon and nitrogen atoms, represents one of the most toxic substances known to chemistry, yet it glows with ethereal beauty when liberated into the vacuum of space. Its presence in cometary spectra provides clues about the organic chemistry that occurred in the stellar nursery where 3I Atlas originated. The abundance of cyanogen relative to other carbon-bearing molecules can reveal details about temperature, pressure, and chemical processes that occurred billions of years ago around a distant star. But the green glow represents only the most visible aspect of a much more complex chemical story. When the Very Large Telescope in Chile turned its powerful spectrographs toward 3I Atlas, it revealed molecular fingerprints that challenge our understanding of how interstellar visitors should behave. The detection of prominent nickel emission lines unaccompanied by the iron signatures that typically occur alongside them creates a chemical puzzle that has researchers reconsidering their assumptions about comet composition. In terrestrial samples and most meteorites, nickel and iron occur together in ratios that reflect the nuclear processes that forged these elements in stellar cores. The cosmic abundance patterns written into the periodic table suggest these elements should appear together in predictable proportions wherever they're found. 3I Atlas seems to have ignored this fundamental rule of cosmic chemistry. The VT observations conducted during the comet's approach phase showed strong nickel emission at 588 nanometers, a distinctive green line that stands out clearly against the complex background spectrum of cometary emission. The same sensitive instruments searched for iron emission at comparable wavelengths and found essentially nothing. The upper limits were so stringent that if iron were present in normal cosmic ratios, it should have been easily detectable. Several theoretical explanations have been proposed to account for this chemical anomaly. Nickel-bearing organic compounds stable in the extreme cold of interstellar space might decompose under solar heating to preferentially release nickel atoms into the gas phase. Space weathering processes operating over millions of years could potentially alter surface chemistry in ways that affect how different elements are incorporated into sublimating ices. The broader chemical portrait revealed by multiple observational campaigns paints 3I Atlas as a visitor shaped by very different formation conditions than objects born in our own solar system. James Webb Space Telescope observations using the NIR SPEC instrument revealed a composition dominated by carbon dioxide, with water vapor playing a surprisingly minor role during the early phases of cometary activity. This carbon dioxide dominance tells a story of formation in a colder, more volatile-rich environment than the region where Earth and the other terrestrial planets formed. Different stellar systems experience different temperature profiles during planet formation, potentially leading to comets with chemical compositions unlike anything in our own Oort cloud or Kuiper belt. The European Space Agency's analysis of these infrared observations notes that the low water to carbon dioxide ratio observed at large, heliocentric distances represents typical early activation behavior where the most volatile ices sublimate first as the comet begins its approach to the Sunday. As 3I Atlas continues toward perihelion, the relative contribution of water vapor to the overall gas production should increase as less volatile ices reach their sublimation temperatures. Production rates of different molecular species provide another window into the visitor's nature. As 3 Atlas approaches the Sun, the rate at which it produces water vapor, carbon dioxide, cyanogen, and other species increases predictably with decreasing heliocentric distance. These production curves follow the expected patterns for sublimating ices, providing strong evidence that we're observing natural physical processes rather than artificial emissions. Yet within this framework of predictable behavior, subtle anomalies persist that keep researchers intrigued. The ratios between different molecular production rates don't exactly match models based on solar system comets. The brightness variations show patterns that suggest either compositional inhomogeneities across the nuclear surface or discrete outgassing events triggered by subsurface processes that remain poorly understood. The amateur astronomy community has played a crucial role in documenting these chemical changes over time. High-quality imaging from experienced observers around the world provides temporal coverage that professional telescopes with their limited observing time and competing priorities cannot match. These observations track changes in coma color tail development and overall brightness that complement the detailed spectroscopic studies conducted by major observatories. Social media has amplified certain aspects of these chemical mysteries, sometimes transforming preliminary scientific results into sensational claims that exceed what the data actually supports. The nickel without iron observation has been interpreted by some as potential evidence of industrial processes or manufacturing signatures, despite the availability of natural explanations for this phenomenon. NASA's official position emphasizes that current observations remain consistent with a natural cometary visitor, albeit one with unusual but not unprecedented characteristics. Agency scientists note that chemical peculiarities are expected for objects formed around other stars, where different temperatures, pressures, and elemental abundances could produce compositions unlike anything familiar from our own solar system. The distinction between exotic and extraordinary remains crucial for interpreting these observations. Exotic chemistry, unusual but explainable through known physical processes, differs fundamentally from extraordinary chemistry that might suggest artificial origins. 3. I-Atlas clearly displays exotic characteristics, but whether those characteristics cross the threshold into the extraordinary remains a subject of ongoing scientific debate. Historical context provides important perspective on these chemical anomalies. Comet 2I Borisov, the previous interstellar visitor studied in detail, displayed its own chemical oddities that initially puzzled researchers. Its carbon monoxide to water ratio differed significantly from solar system comets. Yet detailed analysis revealed these differences could be explained by formation in the colder outer regions of its parent stellar system. The VT analysis of 3I Atlas includes discussion of alternative chemistry pathways that could produce the observed nickel signatures without invoking exotic explanations. nickel carbonyl compounds formed through reactions between nickel-bearing dust grains and carbon monoxide in the cold interstellar medium could potentially explain the preferential release of nickel over iron when heated by solar radiation. As October 2025 progresses and 3I Atlas continues its approach toward perihelion, opportunities for detailed chemical analysis are diminishing. The same solar heating that activates the most interesting chemical processes also positions the comet at increasingly challenging viewing angles from Earth-based telescopes. What if that switching on we observe isn't just chemistry awakening under solar influence, but protocols activating according to some deeper design? The molecules themselves don't reveal their ultimate origins. They simply glow with the quantum mechanical precision that governs all matter, whether natural or crafted by intelligence we have yet to comprehend. Part 8. The Mars Flyby. October 3, 2025. Marks a cosmic appointment that has been millions of years in the making. On this date, 3I Atlas will sweep past Mars at a distance of approximately 30 million kilometers, close enough for the Red Planet's fleet of robotic explorers to turn their instruments toward this interstellar visitor and potentially gather the most detailed observations we may ever obtain of an object from another star system. In the vocabulary of planetary science, 30 million kilometers hardly qualifies as a close encounter. The distance represents roughly 5 times the separation between Earth and Moon, or about 1/5 of an astronomical unit. But in the context of interstellar visitors following hyperbolic trajectories at tens of kilometers per second, this represents an extraordinary opportunity for detailed study during a critical phase of the comet's solar approach. The European Space Agency has announced preliminary plans to coordinate observations using multiple Mars-orbiting spacecraft during this brief encounter window. The ExoMars Trace Gas Orbiter, originally designed to study the Martian atmosphere, carries spectrometers capable of analyzing the chemical composition of 3A Atlas's expanding coma. Mars Express, now in its 3rd decade of operations around the Red Planet, provides additional imaging capabilities and spectrographic instruments that could contribute to our understanding of this cosmic visitor. NASA's Mars Reconnaissance Orbiter, equipped with the powerful high-rise camera system, presents perhaps the most intriguing observational possibility. While the comet will be far too distant for surface feature resolution, HiRISE's exceptional sensitivity and resolution could potentially reveal details about coma structure, dust distribution, and tail geometry invisible to Earth-based telescopes operating through the filter of our planet's atmosphere. The observational geometry during the Mars flyby provides advantages unavailable from any Earth-based viewing location. Mars will be positioned at a different angle relative to the Sun-comet line, potentially revealing aspects of the coma and tail structure that remain hidden from our terrestrial perspective. The lack of atmospheric interference eliminates the seeing limitations and absorption effects that constrain ground-based observations, allowing for potentially sharper images and more accurate photometric measurements. However, significant challenges complicate these observational plans. Mars orbiters were designed primarily to study the planet below them, not distant objects in deep space. Their pointing systems, communication protocols, and data storage capacities reflect these priorities, requiring careful coordination to redirect instruments toward targets millions of kilometers away while maintaining primary mission objectives. The scientific goals for these Mars-based observations focus on characterizing aspects of 3I Atlas that remain poorly understood from Earth-based studies. Detailed imaging could reveal the size distribution of dust particles in the coma through analysis of how they scatter sunlight at different phase angles. Spectrographic observations could constrain the relative abundances of different molecular species, particularly during the active outgassing phase, as the comet approaches closer to the sunday. Neon tail geometry represents another potential target for Mars-based observations. The interaction between the solar wind and ionized gases in the comet's coma creates distinctive tail structures that align with the local magnetic field direction. From Mars's unique vantage point, these ion tail features might reveal details about the comet's gas production rates and the local space environment that would be impossible to observe from Earth. The timing of the Mars encounter adds urgency to these observational plans. 3I Atlas will be experiencing increasingly intense solar heating as it approaches its late October perihelion, potentially triggering the most dramatic outgassing activity of its entire passage through our solar system. The Mars flyby occurs just as this activity is building toward its peak, offering a window into cometary physics that may not repeat for decades or centuries. But practical limitations constrain what even the most sophisticated Mars-based instruments can achieve. The 30 million kilometer separation means that 3I Atlas will appear as little more than a point source to most cameras aboard the orbiting spacecraft. Detailed morphological studies of nuclear structure or precise coma mapping remain beyond the resolution limits of current Mars orbiting assets. Communication delays between Earth and Mars further complicate real-time observation planning. Radio signals take between 4 and 24 minutes to travel between the planets depending on their relative positions in their orbits. This means that observation sequences must be programmed in advance and uploaded to spacecraft memory with limited ability to adjust parameters based on real-time developments in the comet's behavior. Dust storm activity on Mars presents another wildcard factor that could affect observation quality. While major global dust storms occur infrequently, local and regional dust events can reduce visibility and contaminate sensitive instruments. Mission planners must balance the desire for optimal observation timing against the unpredictable Martian weather patterns that could compromise data quality. The data return timeline adds another layer of complexity to these observations. Mars orbiters typically download their collected data to Earth during scheduled communication windows, which may not align optimally with the brief flyby period. Some of the most interesting observations might not reach Earth until days or weeks after the encounter, limiting our ability to coordinate follow-up studies or share preliminary results with the global astronomical community. Despite these challenges, the Mars flyby represents our best opportunity to study an interstellar visitor during its most active phase. Earth-based telescopes will soon lose the ability to track 3I Atlas as it sinks into solar glare, making the Mars observations potentially our last clear view of the object until it emerges from behind the Sun months later, if it emerges at all. The scientific return from these observations could provide crucial tests of competing theories about 3I Atlas's nature. Natural comets undergoing thermal processing near the Sun should display predictable patterns of dust and gas release observable through changes in coma brightness and tail morphology. Any significant deviations from these expected patterns might suggest more exotic explanations for the visitor's behavior. However, it's important to maintain realistic expectations about what these observations can and cannot reveal. The Mars flyby will not involve any direct contact or close approach. The visitor will remain millions of kilometers away throughout the encounter. No samples will be collected, no surface features will be resolved, and no detailed internal structure information will be obtained. The observational campaign also serves as a proof of concept for future interstellar visitor studies. Techniques developed and tested during the 3I Atlas Mars flyby could inform observation strategies for future visitors, potentially leading to more sophisticated and coordinated international efforts to study these rare cosmic wanderers. Contingency planning recognizes that technical failures, communication problems, or unfavorable viewing geometry could limit or eliminate useful data from the encounter. Backup observation strategies using Earth-based telescopes provide some redundancy, though these suffer from increasing solar glare and atmospheric limitations as the flyby period approaches. The Mars encounter timeline compresses the most scientifically valuable observation period into just a few hours or days around closest approach. During this brief window, our robotic ambassadors orbiting the red planet will turn their electronic eyes toward a visitor from another star system, attempting to capture whatever secrets it might reveal during its passage through our cosmic neighborhood. If Mars could eavesdrop on the electromagnetic spectrum during those critical hours, what stories might it intercept? In the static of space, the instruments will listen with the patience of machines and the curiosity of their human creators, hoping to decode whatever messages might be written in the light of a wanderer from the stars. But first, the visitor must complete its appointment with our solar system's fourth planet, carrying whatever mysteries it harbors past the watchful eyes of our Martian sentinels toward its ultimate destination behind the blinding glare of our Sunday. Part 9. Swan R2, the new giant. While 3I Atlas captured attention as an exotic visitor from interstellar space, another cosmic traveler was quietly preparing to steal the show. Comet C 2085 R2, better known as Swan R2. After its discovery in solar and heliospheric observatory data emerged from the depths of our own solar system to become one of the most spectacular cometary displays visible from Earth in recent years. The discovery story begins with the patient dedication of amateur astronomer Vladimir Bezgly, who spent hours examining SWAN instrument imagery looking for the telltale signatures of new comets hiding in the solar glare. On September 11, 2025, his persistence paid off when he identified an anomalous brightening in the data that would soon be confirmed as a previously unknown comet approaching its closest encounter with the Sunday. The SWAN instrument Solar Wind Anisotropes aboard the SOHO spacecraft serves as an unlikely comet hunter, despite being designed primarily to study solar wind interactions with the interplanetary medium. By mapping the distribution of hydrogen atoms created when water molecules are broken apart by solar ultraviolet radiation, SWAN can detect cometary activity that remains invisible to conventional telescopes, particularly for objects too close to the Sun for safe ground-based observation. SWAN R2's emergence from solar conjunction illustrates one of the fundamental challenges in comet discovery. Objects following long-period orbits often spend months approaching the Sun from directions that place them at small angular separations from our star, as seen from Earth. The Holecek effect, named after the Austrian astronomer who first described it, explains why many spectacular comets seem to appear suddenly in our skies fully formed and already active. The comet's official designation as C-25R2 follows the International Astronomical Union's systematic naming convention. The C indicates a long-period comet likely originating from the distant Oort cloud that surrounds our solar system. The year 2025 marks its discovery date, while R2 indicates it was the second comet discovered in the second half of September. By mid-September 2025, SWAN R2 had already reached naked-eye visibility for observers in dark skies, shining at approximately 6th magnitude, the threshold where objects become visible without optical aid under ideal conditions. But unlike many comets that peak in brightness and then fade, this visitor continued brightening as it emerged from its solar encounter and began moving toward its closest approach to Earth. The Astronomy Picture of the Day feature on September 16th highlighted SWAN R2 as a newly discovered comet, visible with binoculars noting its rapid brightening and the spectacular tail development that was making it a favorite target for astrophotographers worldwide. The comet's position near the bright star Spica in the constellation Virgo provided a convenient reference point for amateur observers attempting to locate it in the twilight sky. Observational reports from experienced comet observers began documenting tail lengths extending up to 2 degrees across the sky, roughly 4 times the apparent diameter of the full moon. These measurements, while approximate due to the subjective nature of visual comet observation and the processing techniques used in digital imagery, suggested a tail structure spanning millions of kilometers in physical length. The comet's orbital characteristics tell the story of a visitor from the outer reaches of our own solar system. Unlike 3 Atlas with its hyperbolic interstellar trajectory, SWAN R2 follows an extremely elongated ellipse that carries it from the frigid realm beyond Neptune's orbit to within half an astronomical unit of the Sunday. This represents a journey of decades or centuries during which the comet remained frozen and inactive until solar heating triggered the spectacular display we observe today. Perihelion occurred on September 12, 2025, when SWAN R2 reached its closest approach to the Sun at approximately 0.5 astronomical units, roughly half the distance between Earth and our star. This close solar encounter subjected the comet to intense heating that vaporized surface ices and released the dust and gas that create the visible coma and tail structures. The comet's closest approach to Earth is projected for October 21, 2025, when it will pass within 0.27 astronomical units of our planet, approximately 40 million kilometers away. This represents a favorable viewing geometry that places SWAN R2 at its most accessible for detailed observation during the same timeframe when 3I Atlas approaches its own perihelion. Current brightness estimates place SWAN R2 at magnitude 6 to 7 during mid-September, making it easily visible through binoculars and beginning to approach naked eye visibility for observers with excellent viewing conditions. The continued brightening suggests the comet may reach magnitude 4 or 5 by its closest approach to Earth, potentially making it one of the brightest comets visible during 2025. The Southern Hemisphere provides the most favorable viewing conditions for SWAN R2 during its evening apparition, though Northern Hemisphere observers can still observe the comet low in the western sky after sunset. The comet's position relative to the ecliptic plane and its motion relative to Earth create changing viewing geometries that affect visibility throughout its observing window. Amateur astronomy networks worldwide have mobilized to document SWAN R2's development, creating a real-time observational database that complements professional astronomical studies. High-quality imagery from experienced comet photographers reveals intricate details in the tail structure, including potential disconnection events where magnetic field interactions temporarily separate portions of the ion tail from the main comet body. However, significant uncertainties remain in SWAN R2's orbital parameters due to the relatively short observational arc available since its discovery. Comets can experience non-gravitational forces caused by outgassing that subtly alter their trajectories, making precise long-term predictions challenging until more observational data becomes available. The Minor Planet Center continues to refine orbital solutions as new astrometric observations arrive from observatories worldwide. These measurements will eventually determine whether SWAN R2 follows a closed elliptical orbit that will eventually bring it back to the inner solar system, or whether gravitational perturbations during this passage will eject it permanently into interstellar space. Safety assessments indicate no threat to Earth from SWAN R2's current trajectory. The closest approach distance of 0.27 astronomical units maintains a comfortable margin of safety while providing excellent opportunities for detailed study of this visitor from the outer solar system. Standard precautionary protocols continue monitoring the comet's trajectory for any unexpected changes that might affect these projections. The comet's rapid development and spectacular appearance have made it a favorite subject for public outreach and educational activities. Astronomy clubs and planetariums worldwide are incorporating SWAN R2 into their programming, using its visibility as an opportunity to educate audiences about comet formation, solar system structure, and the dynamic processes that shape our cosmic environment. Professional observatories are beginning to include SWAN R2 in their target lists for spectroscopic and photometric studies. While most telescope time remains allocated to 3 Atlas due to its exotic interstellar origins, SWAN R2 offers valuable opportunities to study the composition and behavior of objects from our own solar system's outer regions. The timing of SWAN R2's appearance, virtually simultaneous with 3I Atlas's passage through our inner solar system, creates an unprecedented opportunity for comparative studies. Two very different types of objects, one interstellar, one from our own Oort cloud, are undergoing similar physical processes under similar solar heating conditions, allowing researchers to examine how formation environment affects cometary behavior. If 3I Atlas represents a scout probing our cosmic neighborhood, why does SWAN R2 arrive like a city-sized herald, announcing something far grander? The universe rarely provides such convenient juxtapositions for comparative study making. October 2025, a month that may reshape our understanding of what travels through the spaces between and within stellar systems. Part 10. Technical speculations, engines, shields, and orbits. The line between the exotic and the engineered often blurs in the realm of speculative astronomy, where unusual observations can inspire extraordinary theories about what might be possible in a universe filled with intelligence we have yet to recognize. 3. I-Atlas and SWAN R2 present characteristics that, while explainable through natural processes, also invite consideration of more provocative alternatives, if only as thought experiments, in the physics of directed motion and controlled energy release. Consider first the question of propulsion. Natural comets follow trajectories determined purely by gravitational mechanics, their paths through space dictated by the inverse square law and the initial conditions of their formation or ejection from distant stellar systems. Any genuine propulsion system would reveal itself through measurable deviations from these predicted orbits. Constant acceleration vectors, attitude changes, or course corrections that violate the principles of ballistic motion. A directed plasma drive operating by ejecting ionized gases at high velocity would create observable signatures in both the trajectory and the electromagnetic spectrum of its host object. The exhaust plume would glow at characteristic wavelengths determined by the composition and temperature of the expelled material. More importantly, the thrust vector would create measurable changes in orbital parameters that accumulate over time into clear violations of Keplerian motion. 3I Atlas displays none of these characteristics. Its hyperbolic trajectory follows the expected path of an object gravitationally unbound to our Sun, with brightness and spectral changes that correlate predictably with decreasing heliocentric distance. The outgassing observed by our most sensitive instruments appears entirely consistent with natural sublimation processes driven by solar heating. Yet the precision of its timing arriving at Mars and Earth's vicinity within a narrow window that coincides with Swan R2's closest approaches challenges statistical expectations in ways that keep theoretical possibilities alive. If coordination rather than coincidence explains this convergence, it would require propulsion systems operating with such subtlety that they remain undetectable by our current observational methods. Electromagnetic shielding presents another area where natural phenomena might mask artificial processes. Comets naturally develop plasma sheaths as the solar wind interacts with ionized gases in their expanding comas. These interactions create complex magnetic field structures that deflect charged particles and shape the characteristic anti-solar direction of ion tails. An active electromagnetic field system would potentially appear very similar to these natural plasma interactions, differing only in the degree of control and directionality it might impose on the surrounding charged particle environment. The key distinction would lie in detecting field configurations that serve no apparent natural function. Magnetic topologies optimized for communication, energy collection, or radiation shielding rather than simple solar wind deflection. Current observations reveal ion tails that behave exactly as expected from natural comet solar wind interactions. The James Webb Space Telescope and ground-based spectrographs detect no anomalous electromagnetic signatures, no coherent radio emissions, no evidence of controlled field generation beyond what solar wind physics naturally produces around active comets. The orbital mechanics of scheduled patrol routes would require patterns of return visits or systematic coverage that distinguish artificial trajectories from the random encounters expected from natural interstellar wanderers. Long-period comets from our own Oort cloud can masquerade as single apparitions even when following closed elliptical orbits. Since their periods often exceed recorded human history, true patrol behavior would eventually reveal itself through repeat appearances at predictable intervals, coordinated arrivals of multiple objects, or trajectory modifications that serve strategic rather than purely gravitational purposes. The 3 confirmed interstellar visitors detected since 2017, 1I Oumuamua, 2I Borisov, and now 3I Atlas, show no evidence of systematic spacing or coordinated activity. Evi's response to our signal hypothesis provides a fascinating thought experiment in the possibility that our electromagnetic leakage into space might have triggered automated responses from dormant monitoring systems distributed throughout our local galactic neighborhood. This scenario would explain the apparent timing correlation between our technological development and the arrival of unusual visitors. However, NASA and ESA maintain that current observational data remain consistent with natural explanations despite their unusual characteristics. The agencies emphasize that extraordinary claims require extraordinary evidence, and the chemical signatures, orbital mechanics, and physical behavior observed in both 3I Atlas and Swan R2 fall within the range of natural cometary phenomena, albeit at the exotic end of that range. The nickel without iron observation in 3I Atlas's spectrum illustrates how anomalous chemistry can be interpreted through both natural and artificial lenses. Industrial processes might selectively concentrate certain elements or isotopes, creating distinctive signatures in the resulting exhaust or waste streams. But the VT analysis includes detailed discussion of natural pathways, nickel-carbonyl chemistry, space weathering effects, and selective sublimation processes that could produce similar chemical fingerprints without invoking technological origins. Color changes and switching on behavior represent another area where natural and artificial explanations compete. Comets routinely display non-linear brightening curves as different volatile species reach their sublimation temperatures at different heliocentric distances. This creates the appearance of discrete activation events that might suggest propulsion systems coming online, when in reality, they reflect the physics of ice sublimation in vacuum. Distinguishing between natural outgassing and artificial emission requires analysis of thrust vectors, acceleration profiles, and energy budgets that exceed what random sublimation processes could produce. Current observations show brightness and spectral changes that correlate exactly with the expected behavior of sublimating ices under increasing solar flux. The hypothetical signatures of genuine engineering would be detectable through several observational channels. Constant thrust acceleration would accumulate into measurable orbital perturbations over time. Attitude control systems would produce periodic variations in brightness or spectral characteristics as different surfaces or components face toward or away from the sunday. Coherent electromagnetic emissions would stand out against the natural radio background of space. Coordinated international monitoring efforts have searched for exactly these kinds of anomalous signatures using radio telescopes, radar systems, and sensitive photometric equipment. The Very Large Array, Arecibo's successor facilities, and other major radio observatories have conducted systematic searches for artificial signals from both visitors. No coherent transmissions, no structured electromagnetic emissions, no evidence of active electronics have been detected. Radar observations attempted by several facilities have also returned null results, though the extreme distances involved make detection challenging even for the most powerful planetary radar systems. The lack of strong radar returns is consistent with natural cometary surfaces composed of low-density ice and dust mixtures, rather than metallic or highly reflective artificial structures. Infrared observations provide another test for artificial versus natural origins. Spacecraft or manufactured objects typically display thermal signatures that differ from natural bodies due to their internal heat sources, thermal regulation systems, or exotic materials. Both 3I Atlas and SWAN R2 show infrared emission profiles consistent with solar heating of natural ice and dust mixtures. The energy budgets implied by various technological scenarios also strain credibility when analyzed quantitatively. Interstellar travel requires enormous energy expenditures, whether for acceleration, life support, or communication across galactic distances. Objects capable of such journeys would likely display signatures of advanced energy systems that remain conspicuously absent from our observations. Mission escalation protocols exist within the international astronomical community for responding to genuinely anomalous discoveries. If multiple independent observatories detected clear evidence of artificial signatures, structured signals, non-gravitational acceleration patterns, or impossible chemical compositions, coordinated follow-up campaigns would mobilize resources from NASA, ESA, and other space agencies to conduct intensive studies. These protocols have not been activated for either 3I Atlas or SWAN R2, indicating that despite their unusual characteristics, both objects remain within the bounds of natural phenomena, as understood by mainstream astronomy. The scientific consensus continues to favor exotic but natural explanations for their observed properties. However, the absence of detected artificial signatures doesn't conclusively prove natural origins, particularly for hypothetical technologies operating beyond our current detection capabilities. Advanced civilizations might employ propulsion systems, communication methods, or material science that produce signatures we lack the sophistication to recognize or interpret. This epistemological limitation, our inability to definitively prove the absence of artificial characteristics, creates space for continued speculation about technological interpretations. The gap between what we can observe and what might theoretically exist allows for scenarios that remain unfalsifiable given our current instrumental capabilities. The psychological appeal of technological explanations reflects deeper human desires to find purpose and intelligence in natural phenomena that might otherwise represent mere coincidence. The precise timing of both visitors' arrivals, their unusual characteristics, and their convergence on our solar system during a period of human technological advancement create narrative patterns that our pattern-seeking minds interpret as potentially meaningful. Statistical analysis of interstellar visitor arrival rates suggests that the apparent clustering of unusual objects in recent years might represent observational selection effects rather than genuine increases in visitation frequency. Our detection capabilities have improved dramatically over the past decade, making it more likely that we would notice objects that might have passed through undetected in previous eras. The 3 confirmed interstellar visitors detected since 2017, 1I Oumuamua, 2I Borisov, and 3I Atlas, each displayed characteristics that initially puzzled researchers but ultimately yielded to natural explanations upon detailed analysis. This track record suggests that unusual properties do not necessarily imply artificial origins, even when those properties challenge existing theoretical frameworks. Computer simulations of interstellar object trajectories indicate that our solar system should receive natural visitors at rates roughly consistent with current observations, assuming reasonable estimates for the population density of ejected objects in our local galactic neighborhood. The timing and characteristics of recent visitors fall within the expected parameter space for natural interstellar wanderers. Yet the possibility remains that some fraction of detected interstellar objects might represent technology so sophisticated that it mimics natural phenomena perfectly, either by design or as an inevitable consequence of advanced engineering that operates within rather than against natural physical laws. Such technology would be virtually indistinguishable from natural objects using current observational methods. The ultimate test of these competing hypotheses may come during the October solar encounters, when both visitors will experience their most intense heating and potentially reveal characteristics hidden during their cooler approach phases. If artificial systems are present, the stress of perihelion passage might trigger responses or failures that distinguish them from purely natural behavior. Ground-based telescopes will lose the ability to observe both objects during their closest solar approaches, creating an observational gap during the most scientifically critical period. This blind spot in our coverage means that the most definitive evidence for or against technological explanations might occur precisely when we cannot observe it. Mars-based observations during 3I Atlas's October 3rd flyby represent our best chance to maintain surveillance during this critical phase, though the limitations of existing Mars orbiters constrain what can be detected even under optimal conditions. The instruments aboard these spacecraft were designed for planetary science rather than the detection of exotic phenomena in passing interstellar objects. If there were genuine machines hiding among these cosmic wanderers, their detection would require observational capabilities and analysis techniques that push the boundaries of current astronomical practice. The distinction between sufficiently advanced technology and natural phenomena may prove more subtle than our current scientific frameworks can reliably distinguish. The question that emerges from this analysis is not whether we have found evidence of artificial visitors, but whether we would recognize such evidence if it were present in forms that transcend our current understanding of what technology should look like when projected across interstellar distances and millions of years of operation. If there were a machine masquerading as a comet, what would we actually see through our telescopes? Perhaps exactly what we are seeing. Objects that challenge our understanding while remaining just plausibly natural enough to avoid triggering the extraordinary evidence requirements that extraordinary claims demand. The universe keeps its secrets while revealing them only to observers sophisticated enough to ask the right questions and patient enough to accept that some answers may lie beyond our current reach. Part 11. Shared Purpose. What could they have in common? In the theater of space, coincidences become conspiracies and timing transforms into choreography when human minds attempt to find patterns in the cosmic chaos surrounding our small world. two visitors arriving within weeks of each other, displaying complementary characteristics and following trajectories that converge on our sun during the same narrow window of time will begin to look less like random encounters and more like coordinated elements of some larger design. If one allows imagination to fill the gaps where data falls silent, consider the possibility that SWAN R2 serves as a mobile depot, while 3I Atlas operates as a nimble reconnaissance probe. In this speculative framework, the massive comet, with its sprawling tail, represents not a natural ice body, but a sophisticated logistics platform, its apparent volatility masking controlled resource management and communication systems. The smaller, more maneuverable 3I Atlas would function as an advanced scout, gathering intelligence about our solar system's characteristics and reporting back to the larger installation. This depot and scout configuration would explain several puzzling aspects of their observed behavior. 3I Atlas's precise timing and trajectory could reflect deliberate navigation toward predetermined coordinates, where SWAN R2 would be positioned to receive data transfer resources or provide maintenance support. The chemical signatures we interpret as unusual outgassing might actually represent controlled emissions, fuel transfer, atmospheric processing, or the byproducts of technological systems operating under extreme thermal stress. Alternative interpretations suggest both objects might be natural bodies that have been opportunistically co-opted by an ancient monitoring network scattered throughout our local galactic region. Rather than purpose-built spacecraft, they could represent commandeered asteroids and comets, their surfaces or interiors modified to serve as platforms for automated systems that activate when specific conditions are met, such as the detection of electromagnetic emissions from developing technological civilizations. This piggybacking scenario would explain why both visitors display characteristics that remain just barely within the realm of natural phenomena. Any civilization sophisticated enough to establish interstellar monitoring networks would likely prefer stealth over detection, using camouflage and mimicry to avoid triggering defensive responses from species they encounter. Converting natural objects into technological platforms provides perfect cover, allowing artificial systems to hide in plain sight among the countless rocks and ice balls that populate interstellar space. The sun itself might serve as more than just a gravitational focus point for these operations. Solar radiation provides an inexhaustible energy source for systems designed to harvest electromagnetic radiation, while the solar wind creates a dynamic plasma environment that could support exotic physics beyond our current understanding. Ion wine streaming away from our star might serve as both communication medium and power source for technologies that operate on principles we have yet to discover. Surveillance grid fantasies envision networks of nodes positioned at optimal locations throughout stellar systems, monitoring the development of planetary environments and the emergence of technological species. The sun's gravitational well creates natural collection points where information from distant sensors could be aggregated, processed, and transmitted to even more distant monitoring stations. Our October 2025 convergence might represent a routine data collection and relay operation. The hunter and harvester dynamic offers a more ominous interpretation of the same timing coincidence. If 3I Atlas represents a predatory system tasked with identifying and neutralizing emerging threats, then SWAN R2 might serve as a resource extraction platform designed to process whatever materials the hunter collects. The scale difference between the nimble scout and the massive processor would reflect their specialized roles in a larger campaign that views past our solar system as either opportunity or threat. Imagery emerging from this speculative framework paints scenes of the small courier spiraling inward toward its rendezvous, while the larger installation unfurls collectors and processing systems in preparation for whatever materials or information the scout delivers. The apparent cometary activity we observe might mask far more purposeful operations: energy collection, matter, conversion, or the construction of temporary infrastructure needed to support extended operations in our vicinity. These scenarios exist entirely in the realm of imagination, unsupported by direct observational evidence, but compelling enough to capture human attention precisely because they provide narrative structure for phenomena that otherwise seem random and meaningless. The human mind rebels against coincidence, preferring explanations that invoke intention and design, even when such explanations require extraordinary leaps beyond available data. The tension between coincidence and choreography reflects deeper philosophical questions about the nature of intelligence in the universe and our ability to recognize it when encountered in unfamiliar forms. If advanced civilizations routinely operate using technologies that mimic natural processes, how would we distinguish between genuine natural phenomena and sufficiently sophisticated artificial systems? The October clustering of events provides real temporal structure around which these speculative narratives can be constructed. Swan R2's September 12th perihelion 3, I-Atlas's October 3rd, Mars flyby 3, I-Atlas's October 29th perihelion and Swan R2's October 21st, closest approach to Earth, create a sequence of coordinates in space and time that could represent either cosmic coincidence or carefully planned choreography. Mythic parallels from human cultural history provide templates for interpreting dual arrivals as omens or harbingers of significant change. Every civilization on Earth has legends of celestial visitors that announced the transition between historical epochs, lights in the sky that preceded the rise of empires, the fall of dynasties, or the emergence of new forms of knowledge and power. Perhaps 3i Atlas and Swan R2 represent a modern manifestation of these archetypal patterns. The recurring refrain that is echoed throughout our investigation is "it a comet, a fortress," or the reply to a message we never knew we sent takes on new meaning when applied to paired visitors rather than singular anomalies. If one represents the message and the other the reply, their convergence might mark the completion of a communication exchange that began when our radio emissions first leaked into space decades ago. But audience guidance becomes crucial at this point in our narrative journey. We have now crossed the threshold into pure speculation, leaving behind the anchor of observational data for the more treacherous waters of imagination and possibility. The facts that ground our investigation, the October timeline, the chemical signatures, the orbital mechanics continue to support natural explanations, even as they inspire more exotic interpretations. The shared mission question assumes coordination where none has been proven purpose, where coincidence remains the simpler explanation, and intelligence where natural processes provide adequate explanatory frameworks. These assumptions reflect human psychological needs for meaning and pattern as much as they reflect genuine scientific puzzles about the behavior of interstellar visitors. Yet the possibility cannot be entirely dismissed that some forms of advanced technology might be so sophisticated that they operate indistinguishable from natural processes, either by design or as an inevitable consequence of engineering that works with rather than against the fundamental laws of physics. Such technology would require detection methods and analysis frameworks that exceed our current scientific capabilities. The ultimate test of these shared purpose scenarios may come during the upcoming solar encounters, when both visitors will experience their most intense heating and potentially reveal characteristics that remain hidden during their cooler approach phases. If coordination exists between these objects, it might manifest during the stress and opportunity of perihelion passage when energy and communication requirements reach their peak levels. The observational gap created by solar glare during these critical phases means that the most definitive evidence for or against coordinated behavior might occur precisely when our instruments cannot observe it. We may emerge from the October silence with refined data about natural cometary processes, or we might find ourselves confronting evidence that challenges our fundamental assumptions about what moves through the darkness between stars. If they share a mission, what mission needs both a scalpel and a factory? The answer might be written in the fire of our sun during the hidden weeks ahead, when two cosmic visitors dance their final steps in humanity's sight before vanishing into the archives of memory and speculation. Part 12. The Relay Hypothesis. A cosmic data drop. In the realm of speculative astronomy, where imagination meets physics, few scenarios capture the sense of cosmic purpose quite like the Relay Hypothesis. The idea that 3i Atlas serves as a data courier, while Swan R2 functions as a processing and transmission center, converging on our sun to complete an information exchange that has been years or decades in preparation. Picture 3i Atlas as the messenger arriving from interstellar space, carrying compressed archives of observations gathered during its long journey through our local galactic neighborhood. Its modest size and nimble trajectory suggest optimization for speed and maneuverability rather than bulk data storage. Yet even a small object could contain vast amounts of information if encoded using sufficiently advanced storage technologies. The unusual chemical signatures we observe might represent not natural outgassing, but controlled data writes, information being inscribed into physical substrates as the courier approaches its designated rendezvous coordinates. Swan R2, emerging from our own solar system's outer reaches, presents the complementary profile of a data center designed for processing and relay operations. Its massive scale and dramatic tail development could mask sophisticated collection arrays and transmission systems optimized to operate under the extreme conditions found near stellar environments. The apparent cometary activity might camouflage directed energy beams, plasma manipulation systems, or exotic communication technologies that function by modulating solar-wind interactions. The Sun itself becomes the crucial third element in this hypothetical relay operation. Our star represents the most powerful energy source within hundreds of astronomical units capable of powering systems that would be impossible to operate using portable power supplies alone. But the Sun offers more than just raw energy. It creates a unique physical environment where gravitational lensing effects, magnetic field interactions, and plasma dynamics might enable communication technologies that operate on principles beyond our current understanding. Gravitational lensing provides one potential mechanism for long-distance communication using stellar-scale infrastructure. Einstein's general relativity predicts that massive objects like stars can focus electromagnetic radiation, creating natural telescopes capable of detecting signals from enormous distances. A sufficiently advanced civilization might position relay stations at gravitational focus points throughout the galaxy, using stars as amplifiers for communication networks that span interstellar distances. The plasma environment surrounding our Sun creates another set of possibilities for exotic physics applications. The solar wind carries charged particles throughout the solar system, establishing electrical currents and magnetic field structures that could potentially be manipulated by advanced technologies. Imagine systems that write information directly into plasma flows, encoding messages in the magnetic field configurations that stream past planets and into interstellar space. Visual imagery of this hypothetical data handoff paints scenes of industrial scale masked by natural phenomena. Swan R2 unfurls collection surfaces disguised as dust and gas clouds, harvesting solar radiation with an efficiency that makes photosynthesis look primitive. Memory storage systems write information into crystalline matrices that can survive interstellar radiation and temperature extremes. The fortress bathes in ion fire while terabytes of compressed intelligence flow between systems operating at the intersection of matter and energy. The concept of harvesting sunlight for energy-hungry data operations reflects the enormous power requirements that any interstellar communication system would face. Broadcasting signals across galactic distances requires energy expenditures that strain even stellar-scale resources. The October 2025 convergence might represent the optimal time window when solar activity, planetary alignments, and receiving station positions create favorable conditions for maximum efficiency data transmission. Earth's radio bubble provides the trigger for this entire hypothetical operation. Since the 1920s, our planet has been leaking electromagnetic radiation into space at increasing rates, creating an expanding sphere of artificial signals that currently extends roughly 100 light-years in all directions. To any monitoring systems positioned within this bubble, our radio emissions represent clear evidence of emerging technological intelligence, a handshake signal that might activate dormant relay networks established long ago for exactly this purpose. The timing correlation between our technological development and the recent arrival of unusual interstellar visitors takes on new significance in this context. If automated monitoring systems detected our first radio transmissions decades ago, they would need time to dispatch courier systems from distant staging areas, navigate interstellar space, and coordinate with local relay infrastructure. The current wave of visitors might represent the response phase of a communication protocol initiated by our own electromagnetic emissions. Yet reality intrudes on these imaginative scenarios with the persistence of observed fact. We haven't detected the narrowband radio emissions that any genuine interstellar communication system would likely produce. No anomalous accelerations have been measured that might indicate controlled propulsion or attitude adjustments. The chemical signatures and physical behavior of both objects remain within the bounds of natural cometary phenomena, albeit at the exotic end of those bounds. NASA's official position continues to emphasize that current observations support natural rather than artificial explanations for both visitors. The agency's scientists note that extraordinary claims require extraordinary evidence, and despite their unusual characteristics, neither 3I Atlas nor Swan R2 display signatures that definitively exceed what natural processes could produce under the right conditions. The if true who sent it question leads down multiple speculative pathways that reveal more about human psychology than about cosmic visitors. Perhaps they represent messages from our own future sent back through some manipulation of spacetime that allows information to travel backward along temporal as well as spatial dimensions. Perhaps they originate from parallel evolutionary lineages that achieved interstellar capabilities millions of years ago and have been monitoring the development of intelligence throughout our local galactic region ever since. Alternative scenarios position both objects as components of an ancient automated network established by civilizations that achieved interstellar capabilities long before Earth formed, then disappeared, leaving only their monitoring and communication infrastructure behind. In this framework, we aren't dealing with active intelligence, but with the technological fossils of species that transcended or extinguished themselves eons ago, leaving behind automated systems that continue executing their programming despite the absence of their creators. The practicality check for any interstellar relay hypothesis involves energy budgets and communication physics that strain credibility when analyzed quantitatively. Broadcasting coherent signals across interstellar distances requires power expenditures measured in significant fractions of stellar output. Even receiving such signals demands antenna arrays with effective apertures comparable to planetary diameters. The infrastructure requirements for genuine interstellar communication networks exceed the industrial capacity of most conceivable civilizations. Yet these limitations apply only to technologies based on current human understanding of physics and engineering. Civilizations that have mastered interstellar travel might operate using principles that make our concepts of energy and communication as obsolete as smoke signals appear to users of fiber optic networks. What seems impossible using 20th century physics might prove routine for species that understand 21st century physics. Just as our current capabilities would seem magical to observers from earlier technological eras, the relay hypothesis provides narrative satisfaction by transforming random cosmic encounters into purposeful intelligence gathering and communication events. It suggests that humanity has crossed some threshold of technological development that makes us worthy of attention from intelligences that monitor the galaxy for emerging species. It implies that we are not alone and not ignored, that our development is being observed and perhaps guided by forces operating on scales we can barely imagine. But it also demands that we accept extraordinary claims based on evidence that remains stubbornly ordinary despite its unusual characteristics. The hypothesis requires coordination, where none has been proven purpose, where coincidence provides simpler explanations, and intelligence, where natural processes offer adequate theoretical frameworks for understanding observed phenomena. The October 2025 convergence will provide crucial tests for any relay hypothesis. If genuine data transfer occurs between our visitors, it should manifest during their closest solar approaches when energy availability peaks and communication windows optimize. The challenge lies in distinguishing between natural cometary activity and the signatures of information processing systems operating under extreme thermal and radiation conditions. What if the handoff completes while our telescopes are blind, hidden behind the glare of our own sun during the most critical phase of this hypothetical operation? We might emerge from the October silence with nothing more than refined measurements of ice sublimation and dust dynamics, or we might find ourselves confronting evidence that our solar system serves as a way station in communication networks that span the galaxy. The relay hypothesis transforms our sun from a simple star into a cosmic post office, our October visitors from random wanderers into mail carriers completing routes that began in stellar systems whose names we do not know. Whether this transformation reflects genuine discovery or merely the human need to find meaning in chaos remains the central mystery of our current cosmic moment. Part 13. The Harvest Scenario. Fuel fields and fires. The sun burns with the accumulated violence of 4.5 billion years of nuclear fusion, converting 4 million tons of matter into energy every second, in a process so fundamental to our existence that we rarely contemplate its raw power. But what if our star represents more than just the anchor of our solar system? What if it serves as a cosmic gas station, a source of exotic fuels and energy forms that civilizations harvest on schedules measured in millennia rather than human lifetimes? Imagine 3I Atlas and Swan R2 as components of an automated harvesting operation arriving at our sun, not by coincidence, but according to patterns established long before human civilization emerged from African savannas. The smaller object functions as a surveyor and coordinator, measuring stellar output characteristics and plasma conditions to optimize collection efficiency. The larger installation deploys collection systems disguised as natural cometary activity, siphoning energy and materials from our star's outer atmosphere using technologies that operate at the intersection of engineering and physics. The harvest scenario requires us to reimagine the spectacular cometary displays we observe as camouflaged industrial processes. Swan R2's magnificent tail, stretching across degrees of sky, might conceal engineered magnetic funnels designed to channel solar wind particles into processing systems hidden within what appears to be a natural coma. The anti-solar direction of ion tails, which we interpret as passive response to charged particle pressure, could actually represent controlled exhaust plumes from sun farming engines operating at scales that dwarf any human industrial enterprise. These hypothetical magnetic collection systems would need to operate with extraordinary subtlety to avoid detection by our increasingly sophisticated instruments. But advanced civilizations might long ago have mastered the art of working with natural forces rather than against them, creating technologies that enhance and direct natural processes rather than replacing them with obviously artificial alternatives. What we interpret as normal comet behavior might actually represent the optimization of natural ion acceleration mechanisms for resource extraction purposes. The physics of such harvesting operations stretch into realms where current human understanding grows thin. Consider the possibility of micro-wormhole networks temporarily stabilized by the extreme gravitational and magnetic field conditions found near stellar surfaces. These microscopic spacetime conduits could provide instantaneous transport for harvested materials across interstellar distances, eliminating the need for conventional propulsion systems to carry collected resources back to distant consumer civilizations. The extreme fields required to maintain such wormhole networks would exist naturally only in environments like stellar coronas, where magnetic field strengths reach thousands of times Earth's surface magnetism, and gravity wells approach the limits where general relativity effects become significant. Our sun's October visitors might be positioning themselves to exploit these unique physical conditions during a brief window when field geometries align favorably for exotic physics applications. Rhythmic pumping operations could follow cycles tied to solar rotation and magnetic field variations, creating cadences of light and shadow that our instruments would record as natural brightness fluctuations. The 27-day solar rotation period establishes natural rhythms in magnetic field orientation and plasma density that sophisticated harvesting systems might exploit for maximum efficiency. October 2025 might represent an optimal harvest window determined by long-term cycles in solar activity and magnetic field configuration. The isotope composition of solar wind provides another potential target for advanced harvesting operations. Our sun produces helium-3 through its fusion processes, creating a lightweight isotope that human fusion researchers consider ideal fuel for advanced reactor designs. Natural solar wind carries this isotope throughout the solar system at concentrations far too low for human exploitation, but sufficiently advanced separation and concentration technologies might extract useful quantities during close stellar approaches. Resource extraction motivations could extend beyond simple fuel collection to include exotic forms of matter and energy that exist only in stellar environments. The extreme temperatures and pressures found in stellar chromospheres might enable the production of exotic matter, states quark-gluon plasmas, magnetic monopoles, or other theoretical particles that could serve as energy sources or manufacturing materials for civilizations operating at galactic scales. Historical parallels with human resource extraction provide templates for understanding how stellar harvesting might operate. Our ancestors followed seasonal migration patterns to exploit temporary concentrations of game animals, edible plants, and raw materials. Modern industrial civilization establishes permanent infrastructure near coal deposits, oil fields, and mineral concentrations that determine the locations of cities and transportation networks. Stellar harvesting represents the logical extension of this pattern to cosmic scales and energy resources. The sound design implications of such operations challenge human imagination. In the vacuum of space, no acoustic waves could propagate from these hypothetical harvesting systems. Yet the electromagnetic signatures might create distinctive patterns recognizable to civilizations that understand how to decode them. Slow bass thrums in radio frequencies, distant crackles as magnetic field lines reconnect and release stored energy, all translated into electromagnetic rather than acoustic phenomena. Station-keeping requirements for any genuine harvesting operation would demand continuous attitude control and position maintenance against the complex gravitational and magnetic forces operating in stellar environments. These requirements would create measurable signatures in the object's trajectories and rotation states that our instruments should be capable of detecting if present. The absence of such signatures in our current observations argues against active harvesting scenarios. Yet we must acknowledge the limits of our detection capabilities when confronted with technologies that might operate thousands of years in advance of human understanding. Systems that maintain position and orientation using manipulation of local magnetic fields might produce signatures so subtle that they remain below our current measurement thresholds. What appears to be natural cometary behavior might actually represent the precise execution of complex industrial protocols. The ethical implications of stellar resource extraction raise profound questions about property rights and territorial claims on cosmic scales. If advanced civilizations routinely harvest energy and materials from stars throughout the galaxy, does our sun represent common property? Or does our presence in orbit around it establish some form of territorial claim? Would harvesting operations necessarily view emerging civilizations like humanity as owners, competitors, or irrelevant biological phenomena? Translation of real comet behavior versus imagined harvesting signatures becomes crucial for evaluating these scenarios. Natural ion tails point away from the sun due to radiation pressure and charged particle interactions that follow well-understood physical laws. Any genuine harvesting operation would need to work within these constraints or produce detectable violations of expected tail geometry and plasma behavior. Our current observations show ion tail behavior that matches theoretical predictions for natural comet solar wind interactions. No anomalous accelerations, no violations of expected tail orientations, no evidence of controlled magnetic field generation beyond what natural plasma physics produces. The spectroscopic signatures we detect correspond to known molecular species undergoing familiar chemical processes under the influence of solar heating. If stellar harvesting operations were active in our solar system, we would expect to detect non-Keplerian orbital signatures as harvesting systems maintained optimal positions relative to changing solar conditions. The absence of such signatures in our tracking data for both 3I Atlas and SWAN R2 suggests that whatever forces control their motion operate through gravitational rather than artificial mechanisms. But the harvest scenario retains its psychological appeal precisely because it transforms random cosmic encounters into elements of a vast industrial enterprise that spans both space and time. It suggests that our sun serves purposes beyond simply providing energy for life on Earth, that our stellar system participates in economic networks that operate on scales we can barely comprehend. The October 2025 convergence becomes a moment of cosmic commerce rather than mere gravitational mechanics, with both visitors playing specialized roles in resource extraction operations that follow schedules established long before human civilization began asking questions about lights in the sky. If the sun is a station in some galactic resource network, how many routes dock here regularly, and what do they carry away into the cosmic night? The answer might be written in the fire and plasma of our star's corona, readable only to intelligence sophisticated enough to distinguish between the natural and the deliberately harvested in the dance of matter and energy that surrounds every star. Part 14. The conflict play. Rescue, retrieval, or purge. In the hidden theater behind our sun's blinding glare where human telescopes cannot penetrate and only imagination can script the drama, October 2025 might witness the final act of a cosmic conflict that has been building since two visitors first appeared in our sky. 3 scenarios play out in the realm of pure speculation, each casting our mysterious visitors in roles that transform them from passive wanderers into active participants in some larger struggle for control, information, or cosmic security. The rescue scenario unfolds as a story of technological salvation, with Swan R2 arriving not as a separate visitor, but as an emergency response to 3 Atlas's distress signals. In this interpretation, the interstellar wanderer represents not a healthy probe, but a damaged scout, its unusual chemical signatures reflecting system failures rather than exotic composition. The nickel emissions without accompanying iron might indicate hull breaches or component failures that are bleeding industrial materials into space as the craft struggles to maintain basic operations. Swan R2's dramatic emergence from solar conjunction takes on new meaning as an emergency deployment. Its spectacular tail development masking the rapid unfurling of rescue equipment and stabilization systems. The massive comet's approach trajectory positions it to intercept 3Y Atlas during the critical phase of solar encounter, when thermal stress and radiation exposure could complete the destruction of whatever systems remain functional aboard the failing interstellar craft. The choreography of rescue operations would require precise timing and coordination that could easily be mistaken for natural gravitational mechanics. Swan R2 would need to match 3Y Atlas's velocity and trajectory while deploying collection systems disguised as cometary outgassing. The operation might involve transferring critical systems, evacuating data storage, or providing power and life support for crew members who have survived years of interstellar travel only to face system failures during their final approach to our Sunday alternative interpretations. Suggest a retrieval scenario where Swan R2 functions as a collector rather than a rescuer arriving to gather intelligence or recover equipment from a probe that has completed its mission. 3I Atlas might represent a reconnaissance platform designed to gather specific information about our solar system, with Swan R2 serving as the mobile storage and transportation system that will carry collected data back to its point of origin. This retrieval operation could involve the physical ingestion of the smaller craft by the larger one, a process that might appear to our instruments as a collision or fragmentation event. But rather than destruction, the apparent consumption would represent the successful recovery of intelligence assets following mission completion. The unusual timing of both objects' solar approaches creates optimal conditions for data transfer and physical recovery, while minimizing exposure to observation from Earth-based telescopes. The logistics of interstellar intelligence gathering might require exactly this type of staged operation, with specialized reconnaissance probes designed to be disposable after single-use missions. The enormous energy costs of interstellar travel make it economically impossible to return small craft to their origins, but larger collector vehicles could efficiently gather multiple completed missions while following trajectories that enable eventual return to base. The Purge scenario presents the darkest interpretation of the October convergence, with Swan R2 arriving not to assist 3I Atlas, but to sanitize evidence of its passage through our solar system. In this framework, the interstellar visitor represents a beacon or communication platform that has exceeded its operational parameters, perhaps by transmitting information back to its controllers, or by revealing too much about its artificial nature through detectable signatures. Swan R2 becomes the cleanup crew tasked with erasing evidence of technological visitation. Before emerging, human intelligence can gather definitive proof of artificial origins. The Purge operation would involve not just the destruction of 3I Atlas, but the dispersion of its remains in ways that make forensic analysis impossible. Advanced disintegration technologies might reduce the probe to constituent atoms, scattering them so thoroughly that no trace remains of their artificial arrangement. The timing of this hypothetical sanitization reflects careful calculation of human observational capabilities and the approaching observational blackout as both objects sink into solar glare. By timing the purge operation to occur when Earth-based telescopes cannot observe the process, the cleanup crew ensures that no human instruments will record the actual destruction and evidence disposal. Each scenario requires us to reimagine the spectacular cometary displays we observe as camouflaged operations involving technologies that operate at the intersection of physics and engineering principles we don't yet understand. The brilliant tails and expanding calm might mask energy weapons, matter disintegration systems, or exotic propulsion technologies that function by manipulating solar wind and magnetic field interactions. But these dramatic interpretations must contend with the persistent reality of observational data that shows no evidence of conflict coordination or artificial intervention. Both objects continue following trajectories determined by gravitational mechanics, displaying spectroscopic signatures consistent with natural ice sublimation and dust emission. No anomalous accelerations suggest active maneuvering. No electromagnetic signatures indicate artificial power systems or communication equipment. Mars serves as our only potential witness to whatever might occur during the critical encounter phases with orbiting spacecraft positioned to observe 3I Atlas during its October 3rd flyby. These robotic observers carry instruments designed for planetary science rather than the detection of exotic phenomena, but they might capture evidence of any genuine interactions between our visitors that exceed the bounds of natural behavior. The European Space Agency's coordination of Mars-based observations represents our best hope for maintaining surveillance during phases when Earth-based telescopes lose track of the visitors due to solar glare. However, the limitations of existing Mars orbiters mean that only the most dramatic deviations from expected natural behavior would be detectable at the distances involved. Communication delays between Earth and Mars further complicate real-time monitoring of any hypothetical conflict scenarios. The 12 to 24-minute signal travel time means that any intervention or response from Earth would arrive too late to affect events occurring on timescales of minutes or hours. We remain passive observers of whatever unfolds in the space between Mars and our Sunday. The psychological appeal of conflict scenarios reflects human tendencies to interpret ambiguous events in terms of familiar narrative structures involving struggle resolution and the triumph of one force over another. These dramatic frameworks provide emotional satisfaction by transforming cosmic coincidence into purposeful action, even when that purpose involves destruction rather than construction. When the lights come back and our telescopes regain their ability to track both visitors, will we count the same number of objects that disappeared behind our sun? Will their orbits' compositions and behaviors match predictions based on natural cometary models? Or will we confront evidence that the universe contains conflicts and resolutions playing out on scales that dwarf human experience and challenge our understanding of what intelligence can accomplish when it operates beyond the reach of seers' human observation? Part 15. The October Silence. The instruments fall silent one by one as both visitors sink into the suns. Overwhelming glare. Observatory feeds flicker and fade. Coronagraphs saturate with light. The greatest show in our cosmic neighborhood vanishes behind a curtain of hydrogen fire, leaving us with nothing but memory speculation and the patient tick of atomic clocks counting down to revelation. In government facilities and university observatories around the world, astronomers hold their collective breath. Social media platforms buzz with amateur theories and artistic interpretations. The absence of data becomes fertile ground for every possibility the human imagination can conceive. In this enforced silence, every scenario becomes equally plausible. Every interpretation carries the weight of potential truth. The palette of outcomes stretches before us like frames from an unfinished film. One object returning altered in color or brightness forever changed by its solar encounter. The other emerging dimmer than expected, or perhaps not emerging at all, consumed by forces we cannot measure or comprehend. Coronagraphs might reveal a delicate ring of fragments, where once there was a single traveler, a testament to some cosmic transaction completed in privacy. Or perhaps nothing changes at all except our appetite for meaning. Our hunger to find purpose in the dance of gravitational mechanics and the poetry of sublimating ice. The reality path leads through patient observation and careful measurement. Swan R2's public window peaks in late September and October, offering amateur astronomers their best chance to witness its spectacular tail sweeping across evening skies. 3I Atlas will emerge from solar conjunction in December if our models hold true, allowing professional instruments to resume their careful cataloging of its chemical signatures and orbital evolution. Current evidence points steadily toward natural phenomena, two remarkable comets whose convergence in time speaks to the mathematics of orbital mechanics rather than the choreography of intelligence. The proven scientific value lies not in confirming our wildest speculations, but in learning about the formation of other star systems, the chemistry of pristine materials from the outer reaches of our galaxy, and the processes that shape objects as they encounter our sun's fierce radiation. Yet in the gap between observation and interpretation, in the silence between data points, stories take root and flourish. We are pattern-seeking creatures living in a universe vast enough to contain both mundane physics and extraordinary possibilities. The October silence becomes a canvas on which we project our deepest questions about intelligence, purpose, and our place in the cosmic order. If an ancient machine kept an appointment at our sun, what would it find in our small corner of space? A young world harboring a curious species, just beginning to reach toward the stars, already filling the electromagnetic spectrum with the chatter of civilization. Perhaps it would find exactly what it was looking for. Or perhaps it would discover something unexpected in the complex symphony of human hopes and fears played out against the backdrop of cosmic time. When December's light returns our visitors to view, when the instruments resume their whispered reports of position and velocity and spectral signatures, we will have our answer to the question that has echoed through 14 chapters of wonder and speculation: Comet Fortress or Reply? Until then, we wait in the October silence, cradled by the gravitational embrace of our sun, wondering what stories the darkness might be writing in languages we have yet to learn to read. The universe keeps its secrets well, but it rewards patience with revelation.